Science is full of bold ideas, some brilliant, some bizarre. What makes science beautiful is not that it's always right, but that it learns from being wrong. Many ideas that once ruled our understanding of the universe now seem almost laughable. Yet in their own time, they made perfect sense. They were the best explanations available, until sharper minds, better experiments, and new tools proved otherwise. In this video, we'll explore 5 big, beautiful theories that once defined science but later crumbled. Each of them carries a timeless lesson about how science evolves and how truth, no matter how deeply believed, can change. 1. Aristotle's theory of motion. For nearly 2,000 years, people believed Aristotle's idea of motion. He argued that to keep something moving, you had to keep pushing it. Stop pushing, and it would naturally come to rest. He also claimed that heavy objects fall faster than light ones, and that fire rises to its natural place in the heavens. It all seemed perfectly reasonable. After all, when you push a box, it slows down when you stop. When you throw a ball, it falls. But Aristotle's logic, while elegant, was wrong. In the early 17th century, Galileo Galilei performed experiments with rolling balls and inclined planes. He noticed that a ball rolls farther on a smoother surface, and concluded that the natural state of motion isn't rest, but uniform movement. Only friction and resistance slow things down. This insight became the foundation for the law of inertia, later formalized by Isaac Newton. Newton's first law stated, "A body in motion stays in motion unless acted upon by an external force." Aristotle's failure gave us an important scientific habit, to search for hidden forces. When you identify them, the universe suddenly makes more sense. 2. Caloric theory of heat. For over a century, scientists believed heat was a kind of invisible fluid that flowed from hot objects to cold ones. They called it caloric. The theory explained why metal felt cold, it was thought to absorb caloric, and why flames warmed your hand. Caloric was pouring out. This idea seemed to work until experiments revealed cracks. When metal cannons were bored out, they produced heat endlessly. If heat was a fluid, where was this infinite supply coming from? In the 1840s, James Joule performed a decisive experiment. He used mechanical paddles to stir water and noticed that the harder he worked, the warmer the water became. Heat wasn't a fluid at all. It was a form of energy. Soon, scientists realized that temperature measures the motion of countless invisible particles. When things get hot, atoms and molecules jiggle faster. When they cool, they slow down. The kinetic theory of heat replaced the old caloric model and gave rise to thermodynamics, the science of energy and its transformations. It explained why friction always produces heat, why engines can't be perfectly efficient, and why perpetual motion machines can never exist. Caloric theory didn't vanish entirely. Its language lingers in phrases like heat flow and specific heat. But we now know heat isn't a ghostly substance. It's energy in motion. 3. The luminiferous ether. In the 19th century, scientists believed that all waves must travel through something. Sound needs air. Ocean waves need water. So surely light must also need a medium. They called this invisible substance the luminiferous ether, a mysterious material thought to fill all of space and carry light waves. But how could you prove it existed? Physicists Albert Michelson and Edward Morley designed a delicate experiment in 1887. They split a beam of light in 2 directions, expecting the Earth's motion through the ether to cause a slight difference in speed. The result? Nothing. No difference at all. The ether wind didn't exist. Scientists tried patching the theory, suggesting that the ether might move with Earth, or that moving objects physically shrank. But none of it held up. Then came Albert Einstein, who solved the problem by removing the ether altogether. He proposed 2 radical ideas. 1. Laws of physics are the same for all observers moving at constant speed. 2. The speed of light is the same for everyone, no matter how fast they move. To make these 2 principles true, space and time themselves must stretch and warp. This became special relativity, a theory that explained everything the ether tried to explain, but with fewer assumptions. The ether disappeared, but the concept of invisible fields remained. Today, we say light is an excitation of the electromagnetic field, a concept far richer and more accurate than the ether ever was. 4. Newton's corpuscles and the wave theory of light. Isaac Newton, one of the greatest scientific minds in history, imagined light as tiny particles, or corpuscles, shot out in straight lines. His model explained reflection and refraction beautifully, but experiments soon revealed something strange. When light passed through two narrow slits, it didn't produce two bright spots. It created a pattern of many light and dark bands. These were the unmistakable fingerprints of waves interfering with each other. So light must be a wave. But then came another mystery, the photoelectric effect. When light shines on a metal surface, it knocks out electrons, but only if the light's frequency is high enough. A bright red beam won't do it, but a dim blue one will. This made no sense if light was purely a wave. The solution came again from Einstein, who proposed that light consists of quanta, packets of energy, later called photons. Light, it turned out, behaves as both a wave and a particle, depending on how you look at it. This duality became a cornerstone of quantum physics. The corpuscle theory failed because it couldn't explain interference, and the pure wave theory failed because it couldn't explain the photoelectric effect. Quantum theory unified both, revealing light's true paradoxical nature. 5. Newton's gravity and Einstein's revolution. For over 200 years, Newton's law of universal gravitation reigned supreme. It said every object in the universe attracts every other object with a force that weakens with the square of the distance between them. It explained everything: the fall of apples, the motion of planets, even the tides. But one small planet refused to obey perfectly: Mercury. Its orbit around the sun wobbled slightly more than Newton's law predicted. Scientists tried every fix they could imagine, tweaking equations, adding hidden planets, but nothing worked. Then Einstein stepped in with a revolutionary idea. Gravity isn't a force acting across space. It's the curvature of space-time itself. Mass tells space-time how to curve, and space-time tells matter how to move. Einstein's general relativity naturally explained Mercury's extra wobble, predicted the bending of starlight by gravity, and showed that time itself runs slower near massive objects. Even today, we use Newton's equations for most engineering and astronomy because they're simple and accurate in weak gravitational fields. But Einstein's theory includes Newton's as a special case and goes beyond it, explaining phenomena from black holes to gravitational waves. The bigger picture. Throughout history, science has built theories, tested them, and replaced them. Theories don't die because they're stupid. They evolve because something better comes along. So how can we tell when a theory's time is up? There are a few clues. 1. Scope. Does a new theory explain more phenomena with fewer assumptions? 2. Precision. Does it survive sharper, more accurate measurements? 3. Unity. Does it connect previously separate pieces of knowledge? 4. Recovery. Does it include the old theory as a special case within its limits? Every great scientific leap follows this pattern. Aristotle's motion gave way to Newton's laws, which expanded into Einstein's relativity. Caloric gave way to thermodynamics. Ether gave way to field theory. Each new idea absorbed the old one, refined it, and explained more of the universe. Science isn't a book of eternal truths. It's a living notebook, constantly rewritten as our understanding deepens. And that's what makes it powerful. Because every time a theory falls, a clearer vision of the universe rises from its ashes.